underground wedge analysis that this failure requires. On the other hand, we will need pre-support of this rock mass. So we need to do something before excavation. So we need some spiles here. We need a smaller, maybe, strip, but 1 or 1.5 in top heading. If we put spiles here, maybe a larger step would be required. Self-drilling anchors would be needed. A grout of the surrounded mass through the spiles also, and immediate saltcrete application to seal the rock mass and constrain it from raveling, etc. from the other kinds of support measures. So let's see. Let's have a quick look of the possible behavior types we can use in this methodology. So we start from the stable ground. So no failure here. We may have some local gravity failures, but the rock mass is compact with limited and isolated discontinuities. Of course, it is not only due to the rock mass conditions, but also due to the tunnel geometry and the diameter of the tunnel in relation and let's say the direction and the rock mass characteristics, the discontinuity direction in relation to the axis of the tunnel. So not only the rock mass quality is governed here, this tunnel behavior type. The second one is a brittle failure, which is rock burst or spalling, so not very intense, only, let's say, rock burst, but spalling may be also here present. The second one is wedge failure, when we have wedge sliding or gravity-driven failures. Here we have insignificant strains. The rock mass is blocky to very blocky. Blocks can fall or slide. And here the stability is controlled by the geometrical and mechanical characteristics of the discontinuities. Here the ratio of the rock mass strength to the in situ stresses is very high, it's larger than 0.7, and we have, again, very small strains. The next gravity-driven failure mode is a chimney type failure. Here the rock mass is highly fractured, maintains, though, a lot of the time its structure, so maybe not immediately around the tunnel, but in the surrounding mass, so it can bridge these gravity-driven failures. So you have this chimney type failure. You don't have very good interlocking. You have an open structure, and with a combination of very low confinement, let's say we are close to the portal or close to a stream, so here all the blocks tend to fall and develop these larger overbreaks. Here the overbreaks may be stopped and bridged by a better quality rock mass, depending, of course, on the in situ conditions. This type can be also be met in a heavily brachiated rock mass, disintegrated rock mass, in a ground with high confinement, let's say in a high lateral stresses, so in a depth where we have high horizontal stresses. The next gravity-driven failure is a raveling ground. Here the rock mass is disintegrated or foliated with practically zero cohesion, and depending on the interlocking, we have two cases, one where we have, let's say, no infilling, and the other one where we also have some infilling material like clay. And here the rock mass can generate immediate rock mass traveling in face and tunnel perimeter. The difference with the chimney type failure lies, of course, in the block size, which is very small here, and the cell support timing, which is very limited to zero. And here we don't have any better quality rock mass in the surrounded zone of the tunnel in order to bridge this failure, and we have continuous traveling. The flowing ground is the same, but here we have the presence of the water, and we have rock fragments flow with water inside the tunnel. Now going to the stress-induced failures. the shear failure, we have minor to medium strains. We have a shallow zone with shear failures around the tunnel perimeter. Here, the rock mass is characterized by low strength of intact rocks, so it's less than 15 to 20 megapascals. And the rock mass structure also reduces the overall rock mass strength. So we have a low GSI here. Strains develop either at the small to medium tunnel cover, so it can happen less than 70 meters. And in case of sheared rock masses, if it is a better quality rock mass, then these strains developed in a larger tunnel cover. The ratio of the rock mass strength to the in situ stresses here are very low. There is very low, so it's between 0.3 and 0.45, and the strains are measured or expected to be medium, 1 to 2.5%. The next one is squeezing ground, where we have large strains due to overstressing. Here the ratio of the rock mass strength to the in situ stresses is very low, it's less than 0.3, and the strains are measured or expected to be larger than 2.5. So here we have either very low rock mass strength and or large tunnel cover. Then the two final ones are swelling grounds, when we may have some swelling minerals inside, like montmolynite, smectite, anhydrite, which swell and deform in the presence of groundwater. We may have some cases where swelling often occurs in the tunnel floor when the support ring is not fully closed, like the one shown in the photograph. And the last case, when we may have some stratified or schistosed weak rocks or weak zones along the rock masses, then we may have some shear zones developed, though in a direction defined by this schistosity. So we have anisotropical strains here. Some photos. Here is a nice photo of chimney type failure, which is filled again with grout. Chimney type failure, a very large one. In this case, you can see in this example a very weathered, highly weathered gneiss in a zone 150 meters depth along a fault, of course. All these photos are cases from tunneling in northern Greece. A raveling grout in brecciated limestone, a sugar cube limestone. And here you can see an overstressed steel sets where we have squeezing ground, a very sheared siltstone, thrusted fleece, heterogeneous tectonically deformed rock masses. Here you can see how the steel sets are bended. In this methodology, the prediction of either we have high strains or extreme squeezing conditions is made through this diagram, which is based in experience from tunneling in a lot of cases. So we have a plot of tunnel convergence, tunnel strains, against the ratio of the rock mass strength to the in situ stress for unsupported tunnels. So this is one case. You can see here how this diagram was developed. You can find it in Hook and Marinos. And now we can proceed to this tunnel behavior chart, which has the experience from these 62 tunnels. This chart is based firstly from the recognition of the identification of the possible structure of the rock mass, then the intact rock strength, and the tunnel overburden. So these are parameters when we can find how the borders of the structurally of the gravity-driven failures, and either they are chimney or raveling or wedge failures, and when these strains may develop in depending on the initial intact rock strength, and then how the GSI may reduce this intact rock strength to the rock mass strength so we can have some calculations of the ratio of the rock mass strength to the in situ stresses. So before describing this chart and give you an example of how this works, just quick reference of where this chart was based. So these 62 tunnels are bore tunnels, and the span of this tunnel is about 12 meters. They were constructed with a conventional method,